Okay, so today we introduced the Darcy-Weisbach equation, which is a way of quantifying the frictional loss of energy in pipe flows. So if we go from point 1 to point 2 in a pipe, where the flow is going from 1 to 2, so say we have Q going from 1 to 2, then the energy equation just tells us P1 on gamma plus Z1 plus the kinetic energy term. I'm going to assume alpha is equal to 1 everywhere, so we'll assume turbulent conditions, plus any energy added by the pump is equal to conditions downstream, so P2 over gamma plus Z2 V2 squared on 2G, energy lost to the turbine plus the head loss. And so this development was something that we did previously when we introduced the energy equation and we did the integration along a pipe. What we're doing now in understanding flow along pipes is we're really looking in detail at this head loss term. This is the loss of energy to friction and other sort of instabilities in the flow. So along a long pipe, say we're going from point 1 to point 2, we have a distance L going from 1 to 2, we're going to write the head loss, the frictional head loss, H sub F, as F L over D V squared over 2G. This is the Darcy-Weisbach equation. The Darcy-Weisbach equation allows us to add this frictional loss into the head loss term. Velocity over 2G, that's just our kinetic energy group. L over D is well defined by the problem. The new quantity here is F, the friction factor. So F is a function of the Reynolds number, and it's a function of the roughness ratio, where epsilon is the roughness of the pipe. This relationship is captured by the Moody diagram, which we're going to look at in our next lecture. But for laminar flow, we can write down exactly that the friction factor is equal to 64 divided by the Reynolds number. That's an analytic solution that we started lecture with, actually, but now I'm just kind of summarizing it in the context of the Darcy-Weisbach equation as a special case defining F. The more general case is for the turbulent flow captured in the Moody diagram. The last thing I'll note in this quick summary is that the total head loss, so the total head loss is equal to H sub F plus the sum of minor losses, which I'll just denote as Ki Vi squared over 2G. These are known as minor losses and are due to inlets, bends, etc. Talked about a couple examples of that in lecture. We'll talk more about that in lecture on Wednesday. Key thing really to work from this lecture, though, is the Darcy-Weisbach equation, how that fits into the energy equation, the introduction of the friction factor. We'll talk about the Moody diagram more in our next lecture. We'll talk about minor losses, and we're going to talk about parallel pipe networks in that lecture as well.